Welcome to Metis, everyone. Wow, are we kicking things off with a bang? I mean, you sent over some absolutely fascinating stuff, and today we're diving headfirst into the world of physics.
Yeah,
Yeah, like the real deal, the how does the universe work kind of stuff.
absolutely.
So our mission today is to unpack what physics really is, right? Like where it comes from, why it's the foundation for understanding, well, basically everything around us, and we'll be tracing its roots back through history, even touching on its connections to alchemy. And then we're going to build a solid understanding by looking at core concepts, energy pressure, Newton's laws, and even peek into some of the most cutting-edge research happening right now.
Yeah, it's going to be a pretty incredible journey, spanning from those early philosophical questions about the nature of the cosmos all the way to the super sophisticated experiments pushing the boundaries of what we know today.
And what's really driving all this is just this basic human curiosity,
That's
right?
hopefully.
All right, so let's start right at the very beginning. What is physics like at its core? What are the big questions it tries to answer?
So at its heart, physics is that fundamental science, trying to understand the natural world, right? It's about figuring out those most basic building blocks of the universe, and most importantly, how they all interact with each other.
So, like the rule book for everything.
Exactly. Think of it as the search for those underlying rules that govern everything from the smallest subatomic particles all the way up to those giant galaxies.
And it's amazing to think about where this quest even began. The material you sent over actually highlights how that drive to understand the world led to the development of chemistry from alchemy, which always seems so mysterious to me. So, what's the connection there between alchemy and what we now call physics?
What's really insightful is that alchemy wasn't just about some mythical quest to turn lead into gold. It was this early form of intellectual exploration, this really broad philosophical and spiritual approach, combining practical knowledge like what we now call chemistry and metalwork with a much wider inquiry into how nature really worked.
It's like a blend of science and spirituality.
Yeah, imagine a time where those lines between disciplines were super blurred. Alchemy brought together elements of physics, medicine, astrology, mysticism, spiritualism, even art, all trying to understand the fundamental principles of the cosmos.
Wow, that's a wild mix.
Right, and they were even trying to achieve things like creating an elixir of life.
Okay, so it sounds almost magical, but did these alchemists actually lay some of the groundwork for modern science?
They did. While those mystical and spiritual aspects of alchemy eventually went their own way, modern science with its rigorous evidence-based approach really started taking hold in the 17th and 18th centuries.
Hmm.
But alchemy's focus on matter and how substances change that directly paved the way for chemistry.
It's like a scientific ancestor.
In a way, yeah. And today, chemistry is often called the central science because it bridges physics, geology, and biology. And that underlying drive to figure out the natural world, the same drive that fueled alchemy, it evolved into the systematic and analytical methods we see in chemistry and physics today. It's a continuous thread of curiosity, always refining its tools and approaches.
That makes the connection so much clearer.
Okay, so let's dive into some of those fundamental concepts within physics. And I think we should start with energy because it's absolutely everywhere. The sources mention that in thermodynamics, we often focus on the change in total energy. Why is that? And what are the big types of energy that physics deals with?
It's a great question, and in thermodynamics, we're mainly interested in how energy moves and changes within a system. It's like tracking money. We're interested in the flow and the transactions, not just how much someone has at one point in time.
So the movement's more important than a fixed amount.
Exactly. So we look at the change in total energy, and for simplicity, we often set the 0 point for total energy at some convenient reference state.
Makes sense.
Now, this total energy can be divided into two main categories based on the scale we're looking at, macroscopic and microscopic.
Macroscopic and microscopic. Okay, that gives me a sense of the size difference. But let's start with macroscopic energy. What defines it, and what are some examples we might encounter? Macroscopic energy is the energy a system has as a whole compared to some external frame of reference. So think a car driving down the road or a book sitting on a shelf. They have macroscopic energy because of their motion or position. And the two key types are kinetic energy, which is energy of motion, and potential energy, which is energy due to position within a force field like gravity.
So kinetic energy is about movement, potential is about position.
Exactly. And there's a formula for kinetic energy. It's Ke equals 1/2 mv squared. So it depends on the mass and the velocity squared. Then there's potential energy for gravity. It's Pe equals mgz, where m is mass, g is gravitational acceleration, and z is the height.
Okay, so those formulas give us a way to calculate these energies.
Right. And there are other things that can contribute to macroscopic energy too, like magnetic fields, electric fields, even surface tension. But those are often simplified or even ignored in basic thermodynamics.
So macroscopic energy is about the system's overall relationship to its surroundings. Now, what about microscopic energy? That sounds like we're zooming way into the molecular level.
It's exactly. Microscopic energy is about the energy stored within the system at that molecular level. It doesn't depend on any external frame of reference. It's all about the individual molecules.
So the energy inside the system, not how it's moving as a whole.
Right. And it's the sum of all the kinetic and potential energies of all those individual molecules. And we call this total microscopic energy. Internal energy, usually represented by the letter U.
And is this internal energy all one type, or are there different forms?
It actually has different components. There's sensible energy, which is directly linked to the motion of those individual molecules, their vibrations, rotations, and translations. This is what we experience as temperature. Higher temperature means more molecular motion, so more sensible energy. Then we have latent energy, which is the energy absorbed or released during phase changes, like when water freezes or boils. But the temperature doesn't change during the phase change.
So sensible energy is about movement. Latent is about changes in state.
Right. And then there's chemical energy stored in the bonds between atoms and molecules, and atomic energy, which is within the nucleus of atoms themselves. For many basic thermodynamic analyses, especially when we're not dealing with chemical or nuclear reactions, we often focus on sensible and latent energy as the main components of internal energy.
So those are the key players in most cases.
Yeah, and the total energy E of a system can be expressed as the sum of its macroscopic and microscopic forms. So E equals Ke plus Pe plus U.
That's a really clear way to break it down. Now, the sources also mention how systems interact with their surroundings by exchanging energy, and they talk about adiabatic systems. What does that mean?
So a system is rarely completely isolated. It can exchange energy with its surroundings in different ways, usually as heat or work. An adiabatic system is a special case where there's no exchange of energy as heat between the system and its surroundings. It's like a perfectly insulated system. Or if a process happens so quickly that there's not enough time for heat transfer.
So no heat flow in or out.
Exactly. We can also classify systems based on whether they exchange mass with their surroundings. A closed system is where mass can't cross the boundaries, but energy can, like a sealed container being heated.
So like a furnace.
Yeah, and then there's an open system or a control volume where both mass energy can cross the boundaries, like a turbine in a power plant, where steam flows in, does work, and flows out.
So closed system energy moves, but no mass transfer control volume. Both can cross the boundaries.
Got it. Okay, moving on. The sources talk about the properties of a system. What are these properties, and what's the difference between intensive and extensive properties? A property is any characteristic of a system that has a definite value when the system is in a particular state. In classical thermodynamics, we often treat the matter in a system as a continuum, meaning we think of it as a continuous smooth substance without any gaps. This works well when we're looking at things much larger than individual molecules. Now, these properties are divided into intensive and extensive properties. Intensive properties don't depend on the size or mass of the system, like temperature, pressure, and density. If you have a glass of water at a certain temperature and pour half of it out, the remaining water is still the same temperature.
So the amount doesn't change these properties.
Exactly. Then there are extensive properties which do depend on the size or mass of the system, like mass itself, volume, and total energy. These are additive if you combine two identical systems. The total mass and volume double. We usually use capital letters for extensive properties except for mass, which is M, and lowercase letters for intensive properties except for pressure P and temperature T. To make comparisons easier, we often use specific properties, which are extensive properties per unit mass, like specific volume, which is volume per unit mass, and it's an intensive property.
So intensive is independent of amount, extensive, depends on it. Okay, now we have these properties, but what defines the state of a system, and what does it mean for a system to be in equilibrium?
The state of a system is defined by the specific fixed values of all its independent properties at a particular time. If any of these properties change, the system is in a new state. It's like a snapshot of the system at that moment. Equilibrium means there are no unbalanced forces or driving forces within the system. If a system is in equilibrium and isolated from its surroundings, its properties won't change. Thermal equilibrium is a special case where the temperature is uniform throughout the system.
So it's balanced and stable internally.
Yeah.
Now let's talk about pressure, something we experience all the time. What is it fundamentally, and how does it behave, especially in fluids?
Pressure, which we represent with a capital P, is the force exerted by a fluid per unit area. The standard unit is the Pascal, or Pa, which is 1 Newton per square meter. In fluids, which includes both liquids and gases when the fluid is at rest, the pressure at any point acts equally in all directions. But when gravity is involved, pressure increases with depth because of the weight of the fluid above. This is described by the equation P equals rho IAH, where rho is the density of the fluid, G is the acceleration due to gravity, and H is the depth below the surface. In solids, the equivalent concept is stress, which can have different values in different directions.
So the deeper you go in water, the more pressure because of the weight above you, which makes sense. Now, the sources mention absolute and gauge pressure. What's the difference, and which one do we use in physics?
Absolute pressure is the actual pressure at a point measured relative to a perfect vacuum where there's no pressure at all. Gauge pressure is the difference between the absolute pressure and the local atmospheric pressure. So gauge pressure of 0 means the absolute pressure equals atmospheric pressure. Gauge pressure can be positive or negative. A negative gauge pressure is also called vacuum pressure. It's important to remember that in most physics and thermodynamics calculations, we use absolute pressure, but a lot of pressure measuring devices are designed to read 0 at atmospheric pressure, so they measure gauge pressure. You need to know what your instrument is measuring and convert to absolute pressure if needed.
So always double check what your readings actually mean. And how do we actually measure pressure? The sources mention manometers and Borden tubes.
Manometers are pretty simple devices that use a liquid column to measure pressure, and they usually measure gauge pressure. A basic U-tube manometer has a U-shaped tube filled with liquid. One end is connected to the pressure source, the other is open to the atmosphere, and the height difference of the liquid in the two arms tells you the pressure difference between the source and the atmosphere. Borden tubes work mechanically. They have a coiled or curved metal tube that straightens or changes curvature when pressure is applied inside. This movement is linked to a pointer on a dial, so you get a direct pressure reading again. Borden gauges are sturdy and can measure both gauge and absolute pressure over a wide range.
Okay, so different tools using different principles to measure this fundamental property. Now let's shift gears a bit and talk about force and motion, the core concepts described by Newton's laws. What's the fundamental relationship between force, mass, and acceleration?
That relationship is captured perfectly by Newton's second law of motion, which is F equals ma. This means that the net force acting on an object is directly proportional to the object's mass and causes an acceleration in the same direction as the force. Simply put, if there's a net force on an object, it will accelerate. The amount of acceleration is directly proportional to the force and inversely proportional to the mass.
So more force, more acceleration, more mass, less acceleration.
Exactly. And we measure force in Newton's mass in kilograms and acceleration in meters per second squared. 1 Newton is the force needed to accelerate a 1 kilogram mass at 1 meters per second squared. So if you have a 10 kilogram object and apply a constant 80 Newton force ignoring friction, it will accelerate at 8 meters per second squared. This means every second its velocity increases by 8 meters per second.
That's a very clear example of how force affects motion.
Yeah.
And the sources mentioned Newton's laws offer different views of force itself.
That's right. Newton's laws define force in a few ways. His first law, the law of inertia, says an object at rest stays at rest, and an object in motion stays in motion at the same velocity unless a net force acts on it. The second law, F equals ma, gives us the mathematical relationship to calculate force from acceleration. And his third law says for every action there's an equal and opposite reaction, meaning forces always come in pairs. A single isolated force can't exist. Also, when multiple forces act on a point, we use the parallelogram law of force addition to find the single force that's equivalent to all those forces combined.
So force is more than just a push or pull. It's a fundamental interaction that governs how things move. Now let's talk about the language of physics mathematics. The sources emphasize how important it is. So how does math help us understand the physical world?
Mathematics is absolutely crucial to physics. It's the framework for building knowledge and describing the world precisely. It lets us create models of natural phenomena and connect those models to experiments. Mathematical equations are a powerful way to connect symbols representing physical quantities through relationships like addition, multiplication, and division. They condense complex relationships into simple statements. In physics, we give these symbols specific meanings like m for mass and a for acceleration, and then math gives us the rules to connect them.
So math is like a universal language for physics.
Exactly. And a key concept is semantic density, which is the amount of meaning packed into a single item like an equation. Mathematics increases the semantic density of physics by letting us create precise relationships between those defined symbols. An equation with many interconnected symbols, each with physical meaning, has high semantic density because it holds a lot of information as a compact form. Like Einstein's famous equation E equals mc squared. It's short, but expresses a profound connection between energy mass and the speed of light.
So a simple equation can hold a huge amount of information. What about connecting those abstract mathematical relationships back to the real world? The sources mention semantic gravity.
Semantic gravity is about how much the meanings of those symbols and their relationships depend on the real-world context. General equations like F equals ma have weak semantic gravity because they apply broadly across many situations. They're not tied to a specific case. But when we put specific numbers into those equations to describe a real event, which is called quantification, the semantic gravity becomes stronger. For example, when we calculate the acceleration of a space shuttle using F equals ma and plug in the actual thrust force and mass of the shuttle, we're connecting the abstract theory to a concrete observation.
So quantification grounds the theory in real measurements, and the sources also mention derivation as a key role of math and physics.
Right, derivation is about manipulating existing equations, using mathematical rules to create new equations. This lets us make explicit relationships that were hidden before. For instance, starting with F equals ma and using the definition of acceleration and momentum, we can derive another equation for force as the time rate of change of momentum. This process of derivation increases the semantic density of physics by expanding the network of concepts and relationships, giving us deeper insights. Ultimately, mathematics gives physics two powers: theoretical development through derivation and connecting theory to data through quantification. This back and forth between abstract and concrete is essential for understanding the universe while staying grounded in observations.
It's a powerful partnership with math bridging the gap between our theories and what we observe. Now, it's easy to get lost in the abstract, but physics is all around us in everyday life. Can you give us some examples of physics in action?
Absolutely. Physics isn't just in labs and textbooks, it's the foundation of our daily experiences. Take electricity. It powers our homes, our devices, everything. Our smartphones use a complex interplay of electricity and magnetism. Density explains why ships float and why it's easier to float in the Dead Sea. Using a wrench relies on torque washing machines. Use centrifugal force inertia is why we need seatbelts, and even writing with a pen uses gravity. And on a smaller scale, fluid dynamics explains why ants can survive falling from heights.
It's amazing how many things we take for granted are governed by these physics principles.
Yeah.
Now, physics is always evolving. What are some of the exciting areas of research today? What are physicists trying to figure out?
Physics is a dynamic field with many unanswered questions. In particle physics, researchers were exploring what lies beyond the standard model. One big area is neutrinos. There's strong evidence they have a tiny mass which solves a puzzle called the solar neutrino problem. The Large Hadron Collider, or LHC, found the Higgs boson. But now it's searching for evidence of supersymmetry, which proposes a deeper symmetry in nature and trying to understand dark matter and dark energy, which make up most of the universe, but we don't know what they are. The 21st century has already seen amazing discoveries like confirmation of solar neutrino oscillation, mapping the cosmic microwave background radiation, discovering the properties of graphene, evidence for a supermassive black hole in our galaxy, the first detection of the Higgs boson, the first observation of gravitational waves, the first image of a black hole, and even the first image of the Milky Way using neutrinos, not light. This shows how dynamic and exciting physics research is always pushing the boundaries of what we know.
It sounds like there are still huge fundamental questions to answer, always expanding our knowledge. So as we wrap up this deep dive into physics, it's clear that it's a vast and relevant field. From the smallest particles to the largest structures and everything in between, physics is at work. We've looked at its history, explored core concepts like energy and pressure, appreciated the power of mathematics, and seen its impact on our lives and the search for knowledge. What stood out to you most from this exploration? What questions or ideas came up? Remember, this is just the beginning of our journey into knowledge, and there's always more to uncover. Maybe our next deep dive can explore one of these fascinating areas that caught your attention today.
I'd love that.
Sounds good to me.